All right, so I've got a 0.70 kilogram object that is vibrating at the end of a horizontal spring. The spring constant, the stiffness of the spring, is 75 newtons per meter, and it's on a frictionless surface. What is the frequency of the vibration? All right, so for a mass on a spring, the things that affect a mass on a spring are the mass and the spring. Oh, crazy. Okay, it's affected by a mass on a spring. All right. I am trying to figure out the frequency. Does this formula solve for that? Well, it solves for period, doesn't solve for frequency, right? But we can easily get frequency because F equals 1 over T, right? So we can easily get that later. Okay, so what we need to do is just plug in our numbers here. We don't even have to manipulate and just solve for T, all right? So that's going to equal 2 pi times the square root of 0.7 divided by 75. All right, so we've got a period of 0.607, but I wanted the frequency, so I'm going to go 1 divided by that number. All right, and I'm going to get that the frequency is 1.6 hertz, or oscillations per second. That means this thing goes back and forth about 1.5 times, a little more than 1.5 times per second. Okay, everybody all right with that? Okay. Okay, and let's look at a pendulum one here. Still math on the spring. Here we go, pendulum. All right, so we have a pendulum that has a period of 3.6 seconds. What's the frequency? All right, so we know T is 3.6, and we have to know that G is 9.81 because they didn't tell us otherwise. All right, so again, whoops, sorry. Yeah, I got ahead of myself. Yes. T equals 1 over F. So F equals 1 over T. All right, so just go 1 divided by 3.6, okay, and we'll have our 0.28. Sorry, let's do a real one. Still a spring. Okay, here we go. This is better. Okay, find the length of a pendulum that has a period of 2 seconds. Yes. Okay. All right, so we have T being 2.0 seconds, and we're looking for the length of the pendulum, okay, and we know that G is 9.81. So the weird thing about a pendulum is that the mass of the bob, that's the part on the end, okay, does not affect the period because all things fall at the same rate. Okay, so it doesn't matter whether you have a heavy pendulum bob or you have a light pendulum bob, they're going to have the same period because the only thing that affects the pendulum, the period of the pendulum, is the length of it, okay, and the acceleration due to gravity. So if I want to solve for anything that's underneath this square root, what do I have to do to everything? Square it, right? I got to get rid of the square root sign. So I'm going to have T squared equals 4 pi squared times L over G. So I'm looking for L, so I'll multiply both sides by G, divide both sides by 4 pi squared, okay, and that'll leave me with L. And so we'll have 9.81 times 2.0 divided by 4 pi squared. I can't believe I just did that. Okay, divided by, what's that? Oh, you're right. Sorry, it is 2 squared. I didn't write that, but it is 2 squared because I wrote it up here. I have not had all of my coffee. I'm going to blame that. Okay, so we get that it is just under a meter long in order to have a period of 2 seconds. Okay, everybody all right with how that works? Okay, I'm going to pick a few questions at random from that worksheet that I want you guys to try, and then I'll move on and talk about Hooke's law and energy after that. Okay. All right, so for number 5 here, okay, we've got a mass on a spring, so we know what K is, and we know it's on a frictionless surface. They tell us the frequency, which we have to use to get period, then we can look for the mass of the object. All right, so T equals 1 over F. All right, so we're going to go 1 divided by 1.5. Must be what, 0.67, right? Yeah. 0.67 seconds will be the period of this object. And then we're going to go to t equals 2 pi root m over k. In order to solve for m, I have to square everything. So t squared equals 4 pi squared times m divided by k. Multiply both sides by k. Divide both sides by 4 pi squared. And I've got m. All right, so we'll have our 115 times 0.67 divided by 4 pi squared, and that should end up as 1.29 kilograms. Yeah. Okay, any others? 13? Okay, so we're looking for the acceleration due to gravity. So we're looking for a little g, okay, in a place where a 0.75 meter long pendulum has a frequency of 0.57 hertz. So we always have to watch. In this last unit, we always have to watch, am I given period or am I given frequency, because it makes a difference. All right, so the first thing I need to do is get the period of this pendulum by going 1 over f, okay, so 1 over 0.57. All right, so the period is 1.75 seconds. I'll keep all those decimals, okay? 1.75 seconds. So I'm looking for g. So again, t equals 2 pi, and this time it's a pendulum, root L over g. If I'm going to solve for anything under the root, then I have to square everything. So 4 pi squared times L over g, and I'm just going to switch t squared and g. So g will be 4 pi squared times L divided by t squared, so 4 pi squared times 0.75 divided by 1.75 squared, okay? And that should give us our 9.6 meters per second squared. Okay, really common things, guys. Accidentally substituting frequency in for period, very common mistake. And I did it earlier, forgetting to square t. Okay, probably that's the most common one. All right, any others we need to go over? Okay, then let's talk about Hooke's law. Okay, so conservation of energy is already something we've done, right? We talked about that in Unit 2, okay? Conservation of mechanical energy in terms like roller coasters, sled going down a hill, okay? That kind of stuff. But that was just looking at gravitational potential energy. Now we need to look at elastic potential energy, okay? Because that's the other kind of mechanical potential energy that is possible for an object to have. For an object to have elastic potential energy, it has to be obviously elastic. That means its shape can be altered, but it will snap back to that original shape. So a rubber band, okay? The bow in a bow and arrow, okay? A bungee cord, okay? Anything like that, okay? All of those things have elastic potential because they can be stretched or bent or somehow have their shape altered, and then will go back to their original shape. A spring is also an example of that. Okay, so what we have to look at here is some things that Hooke discovered about springs and their elastic nature, right? So we're going to look at the relationship between force, spring constant, that's the stiffness of the spring, okay, and the displacement of the spring, right? If I have a spring in front of me and I want to make it smaller, I have to apply a force to it and push both ends together, agreed? The shorter I want to make it, the harder I have to push, logically speaking, right? That's what Hooke's law is all about. Okay? Hooke's law is the mathematical kind of background to that idea. If I want to stretch something, I pull. If I want to stretch it twice as far, I pull twice as hard. Okay? All he did was write it on paper and then got to name it after himself. All right? If you're the first person to put it on paper, it's all yours. All right, and then we need to understand that energy is conserved in simple harmonic motion. So we'll look at, again, a mass on a spring as an example there. We'll also look at a pendulum, except that a pendulum doesn't have elastic potential energy. It has gravitational. So a pendulum is just like a roller coaster. There's no different, right? So we'll look at that elastic rather than gravitational type of energy. All right, so here's what Hooke discovered. If he hung a spring from the roof, it was a certain length. If he hung a mass on it, it got longer. If he hung twice as much mass on it, it stretched twice as far. Wow. Okay, that's what he discovered. All right, and so what he was able to do is relate this stretching displacement, okay, that is how far was it moved from its unstrained or equilibrium position, okay, to when it was when a force was applied to it, right? And what he discovered was that when you do this, you get this relationship. The force in a spring is equal to negative K, the spring constant or the stiffness of the spring, times the displacement of the spring. Okay, that is, again, how far you've stretched it from its unstrained or equilibrium position. What's the negative for? Like, why do we have the negative in here? Yeah, kind of. You're working against the spring constant. Remember, force is a vector quantity, but so is displacement. And I know it's weird to see displacement written as x here, but again, this is not like a change in position. This is a change in length of the spring. Okay, so we're using x instead. All right. If I displace the spring to the right, that is, I stretch it this way, which way does the spring pull? To the left. That's why the negative is here. It ensures that the vector on the spring force is opposite the direction you have pulled it. Okay, so the negative is in there to make sure that those two things always end up opposite each other. Okay, everybody all right with Hooke's law? Mathematically, very easy to use. Okay, just a 3-variable formula. Okay, the only thing that's tricky in there is remembering vectors are important. If I stretch a spring down, it's pulling up. Okay, things like that. Okay, so stated mathematically, F equals negative kx, and like we said, the negative sign is there to ensure the force is always directed opposite. All right, and for a spring, we have to do that because a spring can go either way. A spring can be compressed, that's pushed in, or it can be stretched, that's pulled out. Right? And it's either way, the spring is going to exert equal amounts of force, regardless, of which way you pull it. Right? So if I pull the ball on the spring this way, okay, it'll pull backwards, okay, to the left with this much force. If I push the ball back this direction, the same distance from equilibrium, it's going to be exactly the same magnitude of force going back the other way. Okay, everybody all right with that? So a spring works equally stretched or compressed. Okay? It doesn't make any difference to the spring. It pulls or pushes equally regardless of which direction you deform it. All right. So elastic potential energy is dependent on the spring itself. Okay, how stiff is the spring? Right? The stiffer the spring, the harder it is to change its shape. Okay, and how far the spring is pulled from its equilibrium position. Right. Here's how this relationship works. How many of you remember doing the rubber band lab in Science 10? Okay, where you put the rubber band between the two table legs, between the two desk legs, and you put the spring scale on it, and you pulled it. Okay, that lab finds this. Okay, because in that lab, what you did is you made a graph of force and distance. Okay, and we discovered that when you did this, you got a triangle. Okay, you got a slanted line. Everybody all right with that? Okay, so when we looked in that lab, what we were supposed to do was find the work done. And we found the work that was done by finding the area underneath this line. How did we find the area underneath that line? We did what? Science, yes, we used science. What particular part of it? About triangles. Yeah, that one. Yeah. Did we go 1/2 the base times height? Okay, so we go 1/2 the base times the height. Well, look at what we're doing here. 1/2 the base times the height is force times distance, right? Okay. Now, the force here is the spring force. Hooke's law says this force is K times X. So I'm taking 1/2 of the force, K times X, and I'm multiplying it by X again. 1/2 kx squared. When you found the area of that rectangle, or that triangle, okay, you were finding the work you had done in stretching the rubber band, which was also now the potential energy stored in the rubber band. Okay, we never talked about that in Science 10 because we didn't need to. We were just looking at this from a work energy perspective. Okay, now we can look at that and say, oh yeah, when I do work, I change the energy of the rubber band. I put elastic potential energy into that rubber band. All right, so that's where we get that formula from. It's the work you do in stretching some elastic object. Okay, so if I have a rubber band, I just so happen to have one, okay? Right now, how much energy does this rubber band have? It does? Okay, gravitational, because I'm holding it above the ground. Does it have any elastic potential energy right now? No, because it's not what? It's not stretched. X is 0 in this case. Okay, as soon as I, pull it, I'm not really going to shoot anybody with it. Okay, then it's got now suddenly elastic potential energy. Now X is some value other than 0. Okay, and now it has elastic potential energy because it'll want to snap back to its original shape. Okay, questions on that so far? Everybody's okay with that idea? All right. Can that energy turn into kinetic energy? If I take this rubber band and I put it between two fingers and I put something in it, can it give that thing kinetic energy? Absolutely, right? Okay, so that's what we have to look at. If I've got a mass on a spring and I push the spring in like I am in this picture and I let it go, then the object's going to move this way, right? It's going to shoot outwards. But eventually, what will happen to it? It'll slow down, okay? And it's eventually going to slow down because eventually it's going to get past the equilibrium position. That's the spot where the spring isn't stretched or compressed. And it's going to go past that. Now the spring is going to start being stretched. And once it starts being stretched, it wants to pull back to equilibrium, okay? So the whole reason that a mass oscillates back and forth on a spring is the same reason a roller coaster moves on the track. It's constantly converting potential energy into kinetic energy, and it just oscillates back and forth. Okay, so if we're looking at this in terms of we have a better diagram. I thought I did. Guess I don't. Okay, so let's look at this one instead. Okay, so here's our equilibrium position. Okay, when the ball is back here and the spring can't be pushed anymore this way, it's compressed as far as it'll go. It has all what kind of energy? What kind of energy does it have when the spring is compressed as far as it'll go? Potential, yeah. It's not moving anymore, right? As that ball starts to compress the spring, it slows down, and it compresses the spring as far as it can, and then stops. And then it shoots out the other direction, and it starts converting that potential energy back into kinetic. Okay, eventually it'll get back to this equilibrium position here, and that's where it'll have the most what? Velocity, right? It'll be at its maximum velocity, and thus have the most kinetic energy. Okay, its maximum acceleration is actually here and here, the two maximum strain lengths, because that's where the force is greatest as well, right? F equals m times a. Which is something we're going to get to. You're way ahead of me on that. Okay. All right, so the maximum amount of kinetic energy is at equilibrium. The maximum amounts of potential are at either end. All right. If you look at this, though, okay, it makes kind of a wave shape, right? Just like a roller coaster. Maximum amounts of potential, okay? Maximum amounts of kinetic. We're just converting it back and forth, back and forth. Okay. So that's kind of what we're showing here with this diagram. It's not as good because they didn't identify the equilibrium position as well. Okay? But the equilibrium position is right about there. Okay, so when we have the object out here, so here at the top, on the top position here, okay, its velocity is 0 because the spring has stretched and stretched and stretched and slowed it down and stopped it. Okay, here's where we have all potential energy. As it starts to move back, then we're splitting it. There's some kinetic, there's some potential. The spring is still stretched, but we're not quite at equilibrium yet. And then here, we're at equilibrium. Displacement is 0. The force is 0 here. Okay? The force is 0 because the spring can't push or pull when it's at its unstrained length. Okay? As soon as we move past equilibrium, now the spring is being compressed. Now it's exerting a force this way. The box begins to slow down, okay? And we convert back and forth between kinetic and potential. Right? So this is going to set up just like our roller coaster problems from Unit 2. Okay? The only difference is now instead of having gravitational potential energy, this is now going to be elastic potential energy. Everything else about these problems is exactly the same. Okay? We manipulate for, instead of a height, we manipulate for a displacement. Okay? From equilibrium. We manipulate for a speed in the same way we did before. So it's still EI equals EF, just different kind of energy. All right, so let's okay, so here's a Hooke's law question. Okay, so I have a spring with a constant of 30 newtons per meter, and it's pulled 1.5 meters from equilibrium. What is the restoring force? Okay, so remember, Hooke's law finds the force in the spring, the force that's trying to bring the spring back or restore equilibrium. Okay, that equals negative K times X. Okay, they gave me K, they gave me X, so I should be able to find the restoring force here. All right, so it's it doesn't. I don't have the diagram here, but let's say it was pulled to the right. Okay, so let's say it was yeah. So the displacement here, the 1.5 meters, we're going to say is right. Okay, so we'll have negative 30.0 K times 1.50 meters. All right, and when I do that, I'm going to get negative 45, not meters, newtons. Okay. Okay, that's better. And what happens here? Okay, newtons. The negative represents, in this case, I displaced it to the right, so this is left. All right, try those two. They're Hooke's law questions. Probably leave it at that for today.